was a beautiful afternoon in Colorado, and hundreds of people were out soaking up the summer sunshine. But out of the clear blue sky, nature played a cruel trick.
It happened on a day when there wasn't a cloud in the sky. It was a clear blue sky when, from out of the blue, a bicyclist was struck by lightning. It seemed mysterious to us because where was the cloud from which this lightning originated? This was the first opportunity we thought we had to investigate it, to find out where that cloud was. And to do that, we sought the help of Global Atmospherics in Tucson.
But would Global's system be sensitive enough to pinpoint this mysterious bolt?
We went back and plotted the data for the 3-hour period around the time when this event happened in Vail. If we look here at the screen, we can see the flash over Colorado, and in this case, there was only one flash within 20 miles of this particular location in Vail. This is definitely the one that struck the person.
They found that the single lightning strike in this county at that time of day, on that day, originated in a cloud 10 miles on the other side of this mountain. That cloud was not visible in the valley, so there was no reason for the people, including our patient, to seek shelter. But it is not unknown for lightning to travel some distance, including, in this case, 10 miles, in other instances even more, before it takes a downward dip to reach the ground.
They may appear to come out of the blue, but they are coming out of a thunderstorm for reasons we don't understand. The lightning sometimes will come out sideways from the cloud rather than down below it.
Lightning is capricious. Lightning, which is a beautiful phenomenon of nature, and we all can sit and watch it, but it also can be one of the most cruel phenomena of nature. And this one was particularly cruel because it was hidden.
Lightning is among the biggest natural hazards, killing more people each year in the U.S. than hurricanes, tornadoes, and earthquakes. The paramedics in Lightning Alley are only too aware of this. This storm has already claimed its first victim. Who will be next?
So lightning is a random phenomenon because the charge distribution is not uniform.
Lightning generates tremendous amounts of heat, and with that comes instant water vaporization, which with wet clothing results in an explosive appearance of the clothing. It becomes shredded, metallic objects become fused, such as zippers. And surprisingly, with all this heat that's being generated, there are relatively few burns and some singeing of hair. What we also know now is that there's a tremendous amount of explosive effect or mechanical effect of the lightning that will cause eardrums to rupture, can cause bruising of the heart, contusions of the brain, as well as some skull fractures.
With this sort of power, it's surprising that anyone survives. It's a hot, humid summer's day. Thousands of people are gathered at RFK Stadium for the Freedom for Tibet concert. Suddenly, disaster strikes. One young woman has been singled out from the crowd by a lightning bolt, stopping her heart and paralyzing her lungs. 3 years later, the victim has made a remarkable recovery.
My sister Amanda and I were sitting around here when we came to the concert, and it was a nice day in Washington, which is unusual in June. It was sunny and not too hot, and we were watching the show, and all of a sudden, a huge cloud came out of nowhere without any rain, and a bolt of lightning came out from the sky and hit me right on my head. I was thrown onto the ground, and people near me in the crowd rushed over.
Luckily, one of those people was an off-duty doctor.
She was bleeding from her lips at the time, so we wiped the blood off of her lips, and we started CPR right then. And we also started chest compressions at the same time because she didn't have a heart rate. And it was about 10 minutes after I initially seen her that she regained a heart rate of her own. But at the CPR, she probably would have been brain dead.
Lisa had taken a direct hit from the lightning. As she was rushed off in the ambulance, the medics didn't know she would survive. But why had Lisa been selected from a crowd of over 66,000 people? She wasn't the tallest object. There was the top of the stadium. Even the musicians on the elevated stage would have been an easier target. A discovery made 60 years ago may hold the key to Lisa's mysterious attack. Throughout the 1930s and 40s, the General Electric Company studied the way lightning bolts hit the Empire State Building in New York. They found that the Empire State was hit on average about 23 times a year. But when the team went back and analyzed them, it appears that sometimes a lightning bolt is too weak. It appears that sometimes a lightning bolt is too weak to trigger a streamer until it gets much closer to the ground. By this time, it may have already missed the tallest object.
This makes it possible for a leader, if it's very weak, doesn't have much charge in it, to propagate down towards the ground parallel to, say, a tall building like the Empire State Building. And if it always stays 50 or 60 meters away, it can come all the way down near the bottom before a leader comes off the side of the building at some random point, meets it, and then the lightning attaches to the side of the building. So the tallest thing around is not always what gets hit. Leaders without much charge on them can work their way in between buildings, or can hit the bottoms of trees, or can do things that you wouldn't think otherwise would occur.
The bolt that struck Lisa may have sent down a weak stepped leader, which sneaked past the top of the stadium and the stage. Other people in the audience, as well as Lisa, would have sent up streamers to try and trigger the lightning bolt, but as it zigzagged closer and closer to the crowd, it was only Lisa's streamer that made the fateful connection. As the lightning flashed over Lisa, the searing heat caused second and third degree burns over 20% of her body.
These are the clothes I was wearing when I was hit by lightning. My mom kept them so I'd understand the sheer force of what I survived. The shirt you can see was just totally blown away. And my bra, which had a metal underwire, was melted, the metal, and it caused a third-degree burn under my one breast. Something I never understood, though, was how this could happen if I was wearing 2-inch thick rubber sneakers. I even asked the doctors in the hospital when I realized what happened to me. I later learned that sneakers aren't going to save you if there's a lightning bolt anywhere near you.
Why not?
Because lightning will go right through it.
Okay, guys, why sneakers will not save you? Because your body's going to become polarized, right? It doesn't matter. I mean, she's already sitting on the ground. Unless she's got a rubber ass. Once again, it makes no difference. Right? Any kind of insulating material that you have has nothing to do with it. Your body's going to become polarized. So you start inviting lightning to yourself. It means that your body's going to send out streamers.
Lightning hits the Earth 100 times a second. In the U.S. alone, there are more than 25 million cloud-to-ground strikes each year. About 1,200 of these will hit people, and 100 will be fatal.
All right, so what are we looking at? About 1,200 people get struck by lightning. 100 people die. The ratio is 1 in 12, guys. 11 people usually survive. For every 11 people who survive, only 1 person dies.
The reason why so many people are struck each year is that our fluid-filled bodies provide excellent pathways for electrical charge.
We're damn good conductors. We're not insulators.
The thing about the
Or else the brain would not be able to communicate with the rest of the body.
body is that it's a very good conductor of
We're not like copper, but we're fairly decent conductors.
electricity. Most of the fluids in the body are very salty, and so they conduct very well indeed. And I can show you that on this ball here. These little streamers are just like lightning, except they're very, very small in the way of current. And you can see just how concentrated the electricity becomes. If I put my whole hand, you can see how most of the streamers concentrate around the hand. And it's being conducted down my arm and through my body and away to Earth. Now, perhaps I can make that a little plainer by using this fluorescent tube, and I can conduct
I love this one.
current through the fluorescent tube.
You notice that there's no contact here. All of a sudden the streamers make contact, so it's just going to light up.
If I put the tube like so, you can see current is being transferred through here, along through my right arm, and down and away to Earth. If I do it on this side,
So the streamers from his body once again.
big
All right, guys, if you want to know if you're about to be struck by lightning, all right, here's what you need. Carry this around with you. All right, if it lights up, you're about to be struck by lightning. You got about a minute. All right, I don't expect you guys to do that. You might want to get a pocket size. Obviously, if your crush lights up, which means there's something bad about to happen, or they sell this sort of stuff on the internet, it starts vibrating, which means that you have about a minute to do something. So what's the best thing to do?
in the car.
Just get into your car. If there's no car nearby, just find someone taller, just give them a hug and walk away. All right, just give the streamers to someone else.
Same happens,
More than likely, a taller person is going to get struck, not you.
but on the other half of the body.
The same property that allows us to conduct electricity from the plasma ball also makes us living lightning rods. 3 years later, Lisa is back to normal.
When I feel like I'm taking life for granted, I take a step back and I go, you're extremely lucky because there's a huge chance that you wouldn't have been here, so enjoy today.
Lisa was very lucky. Only a small number of people who suffer a direct hit from a lightning strike live to tell the tale.
So roughly about 1 in 12 dies, but most of them are usually side flashes, guys. Surviving a direct hit is actually not that easy, and she's one of the lucky ones. It's the second time we're discussing this today. All right, so it's recommended that people avoid high grounds during thunderstorms. Explain why. The reason is because the high grounds will be more likely to be struck by lightning. The reason is because the charges will have enough energy to jump a smaller gap than a bigger gap. More than likely, because of it, it's going to strike high ground rather than the low ground or lower ground. And all of a sudden, it gets kind of complicated. So if that logic is correct, we move on to question number 2. If taller objects are more likely to be struck by lightning, why then the Chicago Sears Tower is not the one that gets struck by lightning 100% of the time? All right, so what's the explanation for this one? Why is it that the taller structures are not the ones getting struck by lightning 100% of the time, if that's the case? And this is related to the non-uniformity of the charge distribution under the ground. If the charge distribution is uniform, everything works out. Case in point. They're like capacitors. Let me check to see if the capacitor question is here. Okay, no. I think we discussed that a week before. All right, so if you have select capacitors, straightforward, so this is going to be positive charge, this is going to be negative charge. And then you will have an electric field pointing in the downward direction, so you got your separation distance. So the voltage difference between two absolute charge regions is going to be the strength of the electric field times the separation distance that you're looking at. And the strength of the electric field is going to be uniform. So you got the net charge divided by some constant times the area, which means that you end up getting a uniform surface charge distribution. If this is uniform, the electric field is going to be uniform. Then obviously, high ground versus the low ground, if I just change this, the second surface kind of like that, more than likely it's going to strike the high ground because it's going to have a large enough charge. It's going to have a uniform charge distribution. The gap is going to be smaller, which means that the charge will have enough energy to jump the smaller gap sooner than the bigger gap. Only if you have a uniform charge distribution. All right. Real life looks like that. These are your clouds. You got the high ground, you got the low ground. And obviously this is a smaller gap, but you may have the negative charge distributed here. You may have larger concentrations of things there. So charges are not uniformly distributed. That's the reason why sometimes the lowest ground gets struck more often than the high ground. So it can happen. All right. Question number 11. This is the one that we will get to investigate. So if there's a down power line touching the metal of a car, is it possible to touch the outside of the vehicle without getting electrocuted if you're a passenger inside the vehicle? All right. There's a spelling. Apostrophe is missing. Okay. So the answer to that question is no. You're sitting on the inside. You should be able to touch the outside of the car without getting electrocuted. The best answer that I heard so far, I think Matthew provided a pretty good one, is because there's no electric field inside the vehicle. Electric field is what forces the charge through your body. Net electric field on the inside is zero because the net charge on the inside is zero. So this is the big picture. Okay, so we're looking for a little bit more sophisticated answer than that. So that's what we're going to go for. All right. Boom, boom, boom. Yeah, let me just get out of here. All right, so bringing a positive charge near a positive charge, you have to do work against an electrostatic force. Electrostatic force is a conservative force field, so which means that the amount of work that you do in bringing this positive charge near another positive charge is going to go into the potential energy of this charge, which means that you energize that charge. Now that this charge is potential energy, when you let it go, what happens? The electrostatic force is going to take over, which happens to be a conservative force, so it's going to take the potential energy and convert it into the kinetic energy of that charge. Having said that, does it matter that you bring this positive charge near a positive charge plate directly? Okay, so, all right, let me just change the question. I thought we were going in a different direction. All right, guys, here's a positive charge. I have to do work against a conservative force field like the electrostatic force in order to bring this positive charge near this positive charge plate inside a capacitor. So no matter what that I do is going to go into the potential energy of this charge. All right, so what happens if I release this charge? That potential energy is quickly going to turn into kinetic energy. So it's going to turn into kinetic energy. And notice that the electrostatic force field is going to be constant. The force acting on this charge is going to be constant. The acceleration of this charge is going to be constant. So, which means that whatever happens within this gap becomes motion. All right, does it matter that I bring this charge near this plate, taking the direct path, or does it matter that I'm taking a different route? So the path of motion in this case is not going to matter, right? So when you're dealing with conservative forces, the only thing you have to worry about is the initial and the end points of motion. The path of motion does not matter.